Okay, so this is an iGCSE introductory video about 8C stellar evolution. So really it's about how stars evolve and what happens in stars. So let's start with the middle. The simple idea really of stars are fusion machines. They build most of the atoms we find, the vast majority that is, in the universe today as they release radiation, so like electromagnetic spectrum stuff and particles. Smaller elements such as helium, carbon, nitrogen, oxygen are formed in main sequence stars. So they're stars about the same size as our sun or a bit bigger, and they're in a sort of early part of their life. And so things like helium and beryllium fuse together to form carbon, which is a bigger atom. And then obviously those atoms eventually are released into the universe and they do things like build our bodies. Oxygen, two oxygens could be pushed together to make silicon plus two hydrogens. And those hydrogens would go on to do fusion again. Now, larger elements such as iron, uranium, and such like are made in much larger stars where the fusion forces are increased. So, stars are basically our atom generators. Now, evolution of stars then. So, there's different pathways really, depending on their original size. So, they all start off as a cloud of gas, hydrogen, dust, bits and pieces called a nebula. We then form a baby star called a protostar, where the fusion just starts to kind of come together, switch on, gets hotter, and eventually we've got this glowing main sequence star that looks very much like our star now. Now, here's the big difference. If the star is about the same size as the sun, it eventually becomes a red giant, getting bigger and bigger. In our case, it would then burn everything off our planet. We'd all be dead. And then it would slowly form a white dwarf and eventually a black dwarf and cool down. Now, if though you are bigger, so stars that are between 3 and 10 times the size of our star, eventually become a neutron star. And if you're 10 and above 10 times, you would become a black hole. But in between that, you would have a red supergiant, which is like ours, but much, much bigger. Supernova, which means they literally explode. And that's where you form all these different elements like iron, uranium, and stuff. And then you end up with a pathway of really big ones go black hole, and they suck stuff in and disintegrate matter into energy. Or you just get a neutron star, which is really weird because it's just made of neutrons. So a cupful of a neutron star would weigh the same as the entirety of our planet. Crazy stuff. Hertzsprung-Russell diagrams. Now, these are really quite cool. So now, to understand that, you've got to understand about that there's surface temperature difference and color differences and luminosity differences in stars. And what you've got to learn effectively is this diagram. Now, weirdly, it's got a decreasing temperature surface going outwards and an increasing luminosity. And what we find is that when we have these supergiant or red giants or main sequence or white dwarfs, they form a certain pattern, which is kind of cool. You've just got to learn it and be able to sketch it out. The last thing here, it's a tricky one for triple students, is the brightness of a star at a standard distance can be represented using absolute magnitude. So there's this weird scale where actually when you go up in numbers, you're fainter. And if you go down in numbers in a negative, get more and more negative, you are brighter. Absolute magnitude, M, depends on the luminosity or the brightness of the star. And it's this reverse scale, as we said, and it's an odd system started by the Greeks, and it has lots of complex maths that we don't need for GCSE. You do it later. And what we do is we analyze or compare a star as if it was a standard distance from the Earth. So at 32.6 light years away, or 10 parsecs, or it could be 3 times 10 to 17 meters away. So we put them at a standard distance and decide whether they're brighter or fainter than a reference point. A little bit weird. It's only worth a couple of marks, though. There you go. That's stellar evolution.